Okay, if you're following along at home, you'll want to open up the It's Learning page and find the quiz that goes along with this lecture, Earth as a System, and you can follow right along and answer the questions kind of as we go here. All right, so let's dive in here. Does anybody recognize this picture? What is that? Hey, what's that? Nice, guys. This is Yellowstone. Has anybody been to Yellowstone? No? Oh my goodness. So I took this picture at Yellowstone, the kind of mist rising off of the hot thermal pools. All those colors that you see there are from the different minerals that are in the water and some of the bacteria that are in there. It is a cool place. There's a lot of neat places in America, and hopefully, like kind of as we go in this course, you guys are going to see some pictures of some different places that if you think, oh, I want to travel in my life, I want to go someplace, I want to see America, there's some awesome stuff in our country. Like, we really do have some amazing geology, some amazing places. Other places in the world are amazing too, and I do a lot of traveling, so I'll probably share some of that with you guys as we go along. But Yellowstone's a very unique area. It is very thermally active. If you fall into this, by the way, you pretty much just burn and die. They have had issues in the past with people trying to walk out onto some of those, and the crust will break, and it's boiling water. Like you don't come back out of it, and they a lot of times can't even retrieve the people that go into them. They just kind of slip underneath and literally dissolve away because the water's pretty acidic and things like that. But it's something to see. It really, truly is. And some of the geysers and things we have out there, it's really amazing. But anyway, we're going to talk a little bit about some of the things we'll look at this year. There's a lot of questions that kind of will drive us. Like, what are the fundamental principles that guide geologists as they reconstruct Earth's history? What are the basic kinds of rocks and how are they interrelated? How do geologists unravel the age relations of rocks? How does the lithosphere, which is the rocky part of Earth, Earth's outer layers, relate to the inner regions, right? And how does it move and deform? So we're going to talk about a lot of other stuff along with paleontology to help us understand like how we place dates on fossils and kind of the whole history of our planet, how things got the way they got. So in order to do that, we have to understand that the geological record is like literally like a library of Earth's history. It records everything that's ever happened on our planet, and it's piecemeal. There's missing pieces. You have to kind of put it together. It's a little tricky, but the fact that we can sort it out is pretty darn astounding. You recognize that guy there? That's me. Somewhere around, I tried to figure it out, somewhere around 1981. That's me somewhere out west. I don't look too different, do I? It's pretty much towhead kid. My parents didn't know what to do with me when I was a kid. If we go on a trip someplace, like over the summer, and we'd drive out west or something like that, we did occasionally, they'd stop at a rest area and I was gone. Like if they looked the other way, this is before they had like child leashes where they could like hook it on the back of your jacket or whatever they've got now. I'd take off and be running. If my mom had one of those, she would have yanked that so hard. But yeah, I'd be gone. I think I was up, if I remember right, I was up on top of this rock someplace off of some rest area or something, and my dad had to come and locate me and bring me back because I was gone. So I've always been interested in rocks and geology and the history of our planet. It's really neat to look at the Earth and look at the world through the eyes of a geologist because you see it very differently. It's not just like some strange landscape. Like everything has some meaning, and it brings you back like through the pages of Earth's long history to what actually went on there. Right? So we'll try and unravel a little bit of that. Here we are today. Same guy. Anybody want to guess where that's at? Ooh. That's a tougher one. Nice, that is. So that's a piece of columnar basalt, and it's found in various places around the world. This is actually the bottom of an ancient ocean floor. And if you were to look down on it, it's hexagonally like this perfect hexagon, and it goes just straight down like a big tube. And all of them are like that. This one just kind of broke free and is leaning a little bit. But the ancient ocean floor, as it cooled, it cracked into these bizarro patterns. And it's just something that basalt does, which is what the ocean floor is made up of. Then it got thrust upwards, and then now it's on dry land. So originally that was ocean floor. But the ability to read that record really does change the way you view things. And it definitely changes what you think about, necessarily about yourself, right? And where you fit into all this. So I want to kind of tick back here to when we were talking about the nature of science the other day. By the way, I've really loved reading your responses to that. You guys did a fantastic job. That was great. Keep up the good work on that. Really good stuff. It was super fun to read and hear like kind of your thoughts on what we talked about with the box and all that. It's pretty cool. So I wanted to bring up this point here. It's called Actualism. And next semester when we talk about astronomy, we're going to do something kind of similar to the box activity where you'll probably see actualism in play. And it's a very important philosophical concept in science. It's really a basic philosophical component of all the sciences, but in particular, it's pretty important to geology and paleontology. And all it really says, and it kind of seems stupid to even say it, is that the theory that the facts of geology can and should always be explained, only be explained, by the physical processes that actually happen. In other words, if you're going to posit an explanation for something, it needs to be something that actually exists. Sounds silly, doesn't it? But in the past, we've had situations where we've posited supernatural explanations for physical events that don't exist in the physical realm. In science, the philosophy of science says, well, you can't really do that, right? For instance, for lots and lots of centuries, people have tried to explain geology in terms of mystical or religious or magical processes that don't have any fundamental basis in physical reality. And so we end up with a lot of situations where science and religion are battling each other about things because of the realm of the physical processes we're talking about. So this down here is a picture. I know you don't know what that is because I didn't know what that was. I was in Iceland and just so happened to be going by the Icelandic Sorcery Museum, because there is such a thing in the northern reaches of Iceland, and that's a tilbury. Okay, yeah, the ancient Icelandic sorcery is some really weird stuff. It's very interesting, the history of the people there before they converted to Christianity. The tilbury was a mystical creature that you could kind of create, summon. I'm not sure exactly how it worked, but you made this thing, and it was made out of like sheep fur or something like that, sheep's wool, and I'm not sure what the face is made out of, but I got to see some of these things, and people would put them, apparently sorcerers or sorceresses, would put them inside their clothes and cut a little slit like on their leg where it could drink their blood. And as it grew, as your tilbury grew up, you could set it out at night and it would sneak out of your window and go to your neighbor's house and steal their milk, drink all their milk, and then come back in the morning and vomit it into your milk pail so that you would have milk. You could get the milk from the neighbors. But this is a real, and this was an explanation for how this happened. So, there's things that we look at now and we kind of laugh about, like the tilbury, and I'm sure that's probably humorous or at least laughable for most Icelanders. But there's some strange stuff like that, right? But actualism tells us we can't use a tilbury to explain, where the rocks on the earth came from or what the sequence is, right? So we'll kind of come back to that more as we go, but it's a pretty strange thing. Let's look a little more deeply at actualism. One example of this is when we see ripples on the surface of an ancient rock that's composed of hardened sand, we would assume that they formed in the same way as similar ripples develop today, right? We know the process of making ripples in sand because we can actually see it, right? So that would be the use of actualism to explain this, versus using maybe a supernatural explanation to how the ripples got there, right? Because we actually see them happen, how they form, so it's not much of a leap to say that must somehow harden into rock. And here's some ripples on a beach. Look surprisingly similar to actual ripples compared to the sandstone. I happen to have a rock here I've got with me. That's one side of it. on the other side of it, you guys can see that, there are real ripples on this bad boy. It's kind of a funny story behind this. This came from Ohio, by the way. I was walking down a creek in Ohio, as you do, and I'll let you guys just pass around, you can feel it. So I'm walking down this creek, and I look down, and sure enough, there's this beautiful sandstone, and it's got actual ripples in it. And, well, just to make a long story short, by the time we finished the hike, I was with my wife and some friends. I had like a stack of rocks, I kid you not. Like, the bottom one is about this big, and they just went up to that one little guy on the top, and I was lugging this thing down this creek bed, and I had to climb out of this valley with all these things. But I wasn't leaving home without my ripple marks, because that's pretty cool. You don't see that every day, right? Now, there's a lot you can actually tell from those ripple marks. You can tell, and maybe we'll mess with it a little later in the course, you can tell which way the water was moving when they formed, based on the angle of the ripple marks. In fact, you can tell if it was formed by water or by a sand dune, because they make different kinds of ripples. So it's kind of a neat thing to trace back some of the history like this. Let's look at how some folks have explained the causes of things on our planet. Up until like the early 19th century, catastrophism, the idea that catastrophes created most of the geology that we see, really held sway. We had ideas like the global flood. I'm sure you guys have heard that. It comes out of the Bible, right? Other supernatural forces that formed Earth's rocks. You still hear that today, people talking about, oh, the Grand Canyon must have formed that way because there was a giant global flood. Or, I don't know, the rocks got put the way they are because of a giant global flood. It doesn't work out. Like, there's way too much evidence to the contrary. And nowadays we recognize these concepts as, fundamentally unscientific, right? Now, this doesn't mean that catastrophic things haven't happened, but explaining what we see through supernatural forces, it doesn't fit with the scientific perspective. So along comes this feller named James Hutton. Okay? He was a Scottish gentleman farmer, which basically means that dude was really wealthy, had a bunch of dough, pretty much just chilled out on his farm, a lot of free time. I think he actually became a physician, and just like was very interested in rocks. And so he starts like kind of cataloging all the rocks and the fossils and the things he's finding in the rocks and drawing like layered diagrams. And his famous statement was that the present is the key to the past. In other words, if we wanted to understand everyday things that happened nowadays or things happened in the past, we had to look at things that are happening currently. Okay? So I kind of gave you an example here. Things like volcanoes, earthquakes, weathering and erosion, the settling of sand and mud, ripples, right? Creating and destroying rock, elevating and leveling mountains. Like, everyday processes were doing this. It just maybe was happening on geological timescales, right? Throughout the ages, the Earth has always been changing. And this is one of the ideas that really spurred Charles Darwin on. The idea that maybe the Earth was pretty old. And so a lot of this stuff could have taken a long time to happen. Okay? It really wasn't until like the 1830s that this other guy named Charles Lyell, he's the guy that really popularized, Hutton had all these ideas, but it was Lyell who actually like wrote about them and made it really popular. And I think Lyell's was the book that Darwin read. Right? So take a second there. We're going to, maybe before you answer that, we're going to try and watch a little video clip here.
When you look at a rock, what do you see? Well, you probably see what I see. A rock. Gray, brown, maybe a few sparkles. Nothing too exciting. But to 18th century geologist James Hutton, rocks were more than just rocks. Instead, they were the keys to Earth's history, billions of years of stone shifting, melting, crunching, twisting, and reforming. A history that he discovered in a time when most people believed that the world was 6,000 years old. James Hutton was born in Edinburgh, Scotland, June 3rd, 1726. He was a bit of a floater, studying at several universities throughout his youth. This wasn't a big deal. He had a pretty large inheritance and several farms and was able to live comfortably without finding a specific trade. According to his teachers, he didn't like math very much, but he did have a strong interest in chemistry. He qualified as a doctor and wrote his medical dissertation on the circulation of blood, which he believed correctly, but for the wrong reasons, was being constantly destroyed and renewed. Eventually, Hutton decided that he didn't really want to pursue medicine. He spent some time on his farms, and then he moved back to Edinburgh in 1768 and began to develop his ideas about geology, which also involved renewal and recirculation. In Hutton's time, a lot of people believed that Earth was shaped by catastrophes, like the ones in the Bible. But Hutton thought that Earth actually went through a constant cycle of destruction and renewal. He proposed that rocks and soil are eroded and swept into the sea and then compacted into bedrock before being twisted and turned by enormous pressure. A few years after he first came up with this theory, Hutton discovered evidence for it in a few different rock formations. The most famous of these discoveries was at Sicker Point, a cliff off the eastern coast of Scotland that features layers of red sandstone and greywacke, a darker type of sandstone. The layers were sitting on top of each other, but they were also running in layers perpendicular to one another in what we now call an angular unconformity. He hypothesized that only great amounts of time and great pressure could have offset the rocks, much longer than 6,000 years. And as we now know, of course, he was right. This feature at Sicker Point and several others around Scotland are called Hutton's unconformity in his honor. He also discovered that granite was an igneous rock formed by the cooling of molten lava, by observing tendrils of granite that had made their way into rock like sandstone, which he realized could only have happened at very high temperatures. Hutton believed that this was strong evidence that there was molten rock below the surface of the Earth, and that this molten rock was constantly pushing outward and then melting again. He published his findings in a paper in 1788, but his theories didn't always gain traction because they often contradicted the idea that the Earth was 6,000 years old. Plus, a lot of other scientists' geological theories incorporated the Great Flood described in the Bible. Hutton's ideas did not. But a lot of his work turned out to be accurate, even though he didn't have access to technologies like carbon dating, which would have put actual numbers on the ages of rocks. Hutton also paved the way for future scientists, like 19th century British geologist Charles Lyell, to develop a theory called Uniformitarianism. Uniformitarianism is the idea that the processes that shape the world now also shaped it in the past. So, scientists can work backward and figure out what happened in the past. By assuming that natural laws function in the same way across space and time, we don't need major catastrophes to explain how Earth formed. Instead, we can show that it's the result of slow processes over enormous spans of time. Thanks to Hutton, the picture of our world got a lot more complex. He was wrong about some stuff, but many of his ideas helped shape geological concepts that we still use today. Not too bad for a guy who's famous for saying that the Lord should pity the backside that is, and I quote, clagged to a head that will hunt stones. Thanks for watching this episode of SciShow, which was brought to you by our patrons on Patreon. If you want to help support the show, you can go to patreon.com/SciShow, and don't
Okay, I think I'm unmuted there. There we go. Okay, so in comes the idea of Uniformitarianism, which is a heck of a mouthful, right? Sounds like some different religion or something, doesn't it? It's a heck of a word, and I think it was Lyell that came up with this word, but it really goes along with Hutton's whole idea. And I wrote up there it's mostly correct. It was kind of like the contrast of catastrophism, like everything happened in a great catastrophe, and everybody kind of shifted from that idea over to, well, things have just kind of been playing out in this slow march of time, like gradually processes have been changing the Earth, which for the most part is really correct. Like that's really what's been going on. It does, however, and I put this up here, go just a little bit too far in accepting events that can only really be seen by humans. So there's no doubt that stuff has happened on our planet, and it happened in the distant past, before there were people here, and some of it, no doubt, was very catastrophic. Like some of it was unlike anything we've seen today and experienced today, right? And we can explain these things because we can infer that they occurred by the other evidence, right? But yeah, catastrophic things do happen. Think about the big rock that wiped out the dinosaurs. right? In human lifetimes, we have never seen anything like that. Now, it could happen tomorrow. In fact, I don't know if you guys heard about this today, but I think it must have happened just yesterday, maybe. Do you know what the Arecibo telescope is? Down in Puerto Rico? It's on a mountaintop. It's big. It's like a mile across. It's humongous. It's the whole top of this mountain. It's one of the most famous radio telescopes we have, and it was designed to listen to radio signals. Among other things, the scope is used to listen for ET. It's a big experiment. It does other stuff, quite a bit of other stuff. We can, among some things, we can actually look for near-Earth objects, asteroids that might collide with our planet. And just the day before it got broken, there was a big storm. I think maybe the same storm that came through here, similar type of system, and it knocked a hole. Oh my God, it must be like the size of a skyscraper inside of this radio telescope. It's humongous. It ripped one of the cables off and it went through the side. If you look up a picture on Google, you'll see it. It's pretty impressive. Just the hole itself is impressive, but the entire dish, I think it was in a James Bond movie. Is there a James Bond movie that has a big radio dish in it? You might remember what I'm talking about. It's humongous. I would love to go see it. But anyway, they had just detected a near-Earth object, a big asteroid kind of headed our way, and they were checking to see how far it was, because these are very hard to see. They're very faint, and so we can pick things up in radio signals from them. And they determined, like, oh, it's going to pass by Earth with plenty of room to spare. It's totally cool. But the fact that those things zip by all the time and we never even see them, like, one catastrophic event could be a year away, 10 years away, a million years away, 10,000 years away. Like, we don't know. I mean, that stuff's out there floating around. There's less of it than there was when the dinosaurs were around, but it could happen, right? So anyway, back to the uniformitarianism. It's mostly right? But definitely in the past, things were a little different, and we have to accept that. Now, how do we know that? Okay. Well, actualism is really what helps us know that. In fact, for instance, early Earth, our moon was much closer to the Earth when Earth first formed. It would have looked ungodly huge. Like, it would have been really big. The moon has slowly slipped away from us. Every year it gets a little bit further away. I know, it's kind of sad, isn't it? Like, we're losing our moon, come back, right? It'll be here for our lifetimes, no worries. Yeah.
Whatever, like fly away?
Fly away completely? No, it's always going to be gravitationally attached to us. I think the last time I was reading up about that, it's going to continue to slip away, and at some point, maybe start to come back. But it's going to get pretty far away. At some point, it'll be far enough away that it'll no longer eclipse the sun like it does. There'll be more sun showing around when we have an eclipse go by. But the reason we're losing it, which is a totally different topic, is because the Earth's oceans, which cause friction against the Earth because the tidal bulges. So we pull on the moon pulls on us. Because, I almost need to draw a diagram, because the Earth spins, and the moon is here, the moon pulls, and our water, since it's loose, kind of heads up towards, pushes out, bulges out towards the moon. But since the Earth is spinning, it pushes that bulge of water forward, ahead of the moon a little bit. Well, that bulge of water is big enough, it's got its own gravity, and that tugs on the moon, which speeds the moon up. And if you go faster in your orbit, you slip away. If you slow down in your orbit decays, and eventually you spiral in and crash into Earth. So I guess it's good it's going the other way, right? It's definitely good it's going the other way. But the moon's had its effect too. The moon tugging on the Earth has actually slowed our rotation. Originally, our day would have been much shorter, like 12-hour day. I mean, day and night, whole day long. And it's slowly slowed us down to the point where now, like every, couple centuries or whatever, we got to add a second or something to our time because it's slowing down the rotation of the Earth on its axis. So we know some things were different in the past, but we use actual inferences by what we understand about nature to describe that, to understand it, right? There's no need to have a supernatural explanation for that physical event. I think I put some examples up there. Yeah, all of our iron, we wouldn't have, we'll talk about that later on, but we wouldn't have desks and knives and tables and things like that if we couldn't explain this stuff the way we do. Yep. Okay. But the big one is that, you know, the natural laws really haven't changed, but things might have been operating a little differently. Okay. We're going to roll into, I think, wait a minute. Yeah. I'm still recording, yeah. So, let's take a look at rocks and minerals. One of the first things we're going to do in here is start to identify rocks and minerals. And then as part of your collections when we go outside, you guys can try and locate some of these and identify them and put them in your collections. And at some point, if we collect enough good stuff, good material, we'll pull out the rock tumbler and actually polish this stuff. And I'll let you guys make some necklaces and jewelry and stuff out of it, which is really pretty cool. Make jewelry out of a rock that we picked up out of a tree. So we'll try and do that. We've got to collect some material, but you have to know something about what you're collecting to use it. So let's talk about the difference between a rock and a mineral. And we'll talk more about this next time, but rocks are typically composed of a bunch of different minerals. They don't have to have minerals, but it's a simple way to think about the difference. Here's a piece of granite, and if you look up here, all those little gray things that are in there, those little gray things are actually quartz crystals, which is a mineral. It's pure, it's a pure mineral, SiO2. And it looks gray just because the light doesn't pass through it. It would be clear. If you broke one of those little guys out, it would actually be pretty clear. The pinks and the whites are types of feldspar mineral. And then the blacks are a type of flaky, flat mica called biotite. So that rock is made up of a whole bunch of individual crystal minerals. But a mineral itself has to be naturally occurring. It's got to be inorganic, like not made from living things, right? Like non-carbon based. So, well, we'll get to that in a second. It's got to be solid, so it can't be liquid. And it has to have a crystalline structure. So it usually looks crystalline in all the same stuff. In other words, the same elements. Not a mixture, but bonded together elements that are the same. Let's see if we can figure some of these out. Okay, I have up here gabbro, which I brought some from a quarry in Wisconsin. Uh-oh. There we go. There's a big hunk of gabbro right there. Take a close look at the gabbro. You actually see the drill mark where they drilled in the quarry. Do you see the slight different colors in here? What do you think? Rock or mineral? Rock would be right. If you're thinking rock, gabbro's a rock. It's actually made up of a bunch of different minerals. It's a little hard to see on mine because they all look the same color. But there's a bunch of different minerals in there making up that rock gabbro. How about coal? Mineral? It's all the same stuff. It's all carbon, right? What's coal made from, though? This isn't charcoal like you throw in your grill, by the way. This is like coal that we dig out of the ground in a coal mine. There's actually a difference. So coal forms from the dead remains of things like ancient plants that fell into swamps and got buried. So totally organic formation. Other than that, it would be a mineral. So coal is actually a rock. Have you guys ever seen coal in your stocking? No? Nobody gets coal in their stocking anymore? I was upset. My parents never gave me coal. I just want some coal. There's some bituminous coal. This is stuff we dig up out of the earth. You'll be surprised because unlike other rocks, it's crazy light. It like almost feels like air. Yeah.
I've heard that this place out to the sea that used to be coal mine and like some of those trails where you're riding like people.
Yeah, absolutely. I've been down there in places in Tennessee and found lots of coal. And just because, like, why wouldn't you sitting around the campfire at night? Like, what's it like to really burn coal? Because we don't burn coal anymore, right? I mean, like, regular everyday people don't burn coal. We do in our power plants. So I stuff a bunch, you know, in the campfire. You would not believe how bad that smells and how much smoke. Like, it's horrible. I can't imagine anybody heating with coal. Like, once you do that, you're like, okay, environmentalism is definitely right. We should not be burning this stuff. Like, nobody should be breathing this. It's terrible. It's like this black, horrible, choking smoke. But boy, once you light a piece of coal on fire, it's not like charcoal from your grill. That's totally different stuff. When you light the rock on fire, that thing just glows and glows, and it looks like a burning rock. It's pretty neat. Like, everybody should do it. Maybe we'll light one up sometime down in the lab under the fume hood, because it's really stinky. It's actually really hard to light. You can't just dump some lighter fluid on it and strike it up. You've got to get it pretty hot, pretty dry for it to start going. But yeah, it's got tons of energy in it. Well, you can see why people used it. Definitely works. How about, it's a good one, basalt. Basalt looks like this. Yeah, it's kind of both. I brought a piece of pure basalt up here. Really no basalt on that. Yeah. Basalt looks all ropey like this because oftentimes it flows out of lava from a volcano. So even though it looks pretty homogeneous, it's actually made up of individual little crystals that are different. So it can be tricky. Like some of this you just kind of memorize after a while. And the last one up here I've got icicles. What do you think about the icicles? Is it made of all the same stuff? H2O, right? Same chemical composition. Is it made of anything organic? Any living stuff in there? No. Okay. Is it occur naturally? Is it a crystalline solid? Yeah, it's pretty crystalline. See ice crystals? Mineral. When you eat icicles, you're eating a mineral. Now, if you're eating ice cubes, I guess you're not eating a mineral because it's man-made, right? It's like the difference between having a cubic zirconium ring and an actual ring of diamond. So this would actually be a mineral. I'll show you some breakdown here. So that's what basalt looks like under a microscope. If you had a very thin slice, you could pass light through. So basalt is definitely a rock. Okay, we're going to go through the types of rocks. And I think the last question you have on there, and we'll put it up at the end here to help you out, is the rocks in the rock cycle. The first rock in the rock cycle we'll talk about is igneous rock. And I don't remember my Greek mythology, but I think Igni was the god or the goddess of fire. I think I got that right. So these rocks come from fire, is kind of what we're saying. They come from molten liquid rock hardens into new rock. So think volcano, right? These are volcanic rocks is the other way we call them. They cool down and they recrystallize. They're usually composed of bunches of different types of mineral grains all bonded together. They oftentimes look like this one here, which is diorite. This is granite, similar. You can see all the cool crystals in there. It's some polish on this side. You've probably seen granite tabletops, right? That came from igneous rock underneath the earth, cooling very slowly, not erupting, but cooling slowly. So I put two different examples up here. There's two types of igneous rocks. We'll do this again in lab next time we're down there. Intrusive and extrusive. So an intruder comes inside, right? And an extruder is what you do with your toothpaste. So it comes out. So extrusive rocks are any time the lava spills out onto the surface, whether it blows up or it just kind of oozes out. So these things, looking at these two things, the liquid stuff that's underneath the earth that cools versus the stuff that spills out on the surface, which one cools faster? The stuff that comes on the surface, right? Sometimes it spills right out into the water, cools really fast. And so you end up with two different situations. You end up with this beautiful diorite, which this stuff cools very slowly. I mean, you maybe even have thousands of years to cool underneath Earth's surface. And you get these big, huge, beautiful grown crystals. Versus this stuff, which cools super fast, it actually becomes a glass. It cools so fast that no crystals form at all. So this is a volcanic glass. This is obsidian. This is what we make arrowheads out of, by the way. So tabletop versus arrowheads. And you know what? Sometimes these can be exactly the same stuff. Same composition and everything. All the minerals are the same. Right? All the elements are the same. And you get two totally different things just on how they cool. Ooh, there we go. The next one on our list is the sedimentary rock. So we've got the fire rock. The sedimentary rock, think sediment, that's like dirt, right? This is stuff that settles. That's where the word comes from, settling rock. You get a bunch of little pieces of stuff, it settles in some water or in some air, and it gets compacted, and then it turns into solid rock. So the sandstone that I showed you, that had the ripples in it, that's a sedimentary rock. It's usually made up of bits and pieces of other rocks, okay? Kind of glued together. There can be different glues, and we'll talk about some of the glues. It can be glued. It's glued together usually with different stuff. It's a whole process. Now, what else do I bring up here? Here we go. So I brought two other examples up here because there's kind of maybe even another kind I didn't put up here, but clastic is broken bits of stuff, like the sandstone. It's little broken bits of sand all put together and rehardened. Or you could have bigger stuff all hardened together, kind of looks like pavement. So think of clashing or bashing stuff together. Bio is life, right? So biogenic stuff is like coal, or even this limestone, this coquina limestone. It's a whole bunch of shells. If you look closely at this one, there's a whole bunch of shells in there. This came from Florida. So a lot of the rock in Florida is actually shells that have been compressed together. In fact, they grind that stuff up and make their roads out of it. It's kind of cool. Like you drive down Florida and you're like, that pavement's got shells in it. So it gets that. There's so much of it. And then the last one, these are the hardest to tell apart because they look like igneous rocks. The chemically made ones. Turns out that you can get a sedimentary rock if chemicals, just not molten, but just chemicals, move through another rock and fill in a space and harden. And it's called the chemical sedimentary rock. They look really weird. 99% of everything you pick up in the creek is going to be this stuff called chert. Ours is typically pretty orange. It comes in every color imaginable. This is what the Native Americans in Indiana made their arrowheads out of. This is what they made all their tools out of. And I broke this one so you can see how I dulled it a little bit, but you can see how sharp it kind of gets. You can see the different colors in it. That's a chemical process where it seeps through the rock that's there, fills in a spot, and hardens into new rock. So it wasn't molten like out of a volcano. It was just moving through the ground. Okay? And there's lots of different types of these rocks. I just gave you a couple examples. But those are hard to tell apart a little bit. Okay. All right, let's talk about what some of these sedimentary rocks look like in nature. Sedimentary rocks are some of the most useful rocks for figuring out the history of Earth, for turning back the pages. Because they quite literally look like pages in a book when you look at them. Anybody recognize that spot? That's here in the United States. Oh yeah, very good. A very famous spot over there. It's actually the Grand Canyon. It's a small slot canyon off to the side inside the Grand Canyon. My wife and I rafted a raft. A friend of mine owns or works at a rafting company. I don't know if you guys have had her, and she talked about this. Did she? Yeah, if she starts talking about this, I start to get in trouble because she's like terrified of rafting now. Because we did almost drown. I've almost drowned a few times in my life, but it was like really serious. So my buddy Mac works for a rafting company, and his job is to raft people down the Grand Canyon. It is so cool. And it costs thousands of dollars to do. He calls me up one day, I've talked to him in like 20 some years. He's like, hey, I got a couple of extra spots, I can give them to you for cost. I was like, are you serious? Like, because it's like people pay. We went on this trip with him, and the CEO of, what was it, Sony or something like that, was on this trip. Yeah, so it's like my wife and I, like two lonely little teachers, and like the CEOs of these huge companies that are paying all this money, and they literally rafted us down this river and like cooked steak dinner for us along the way. It was the most glamping I've ever done in my life. It was so bizarre. It was Panasonic, that's who it was from. He worked at Panasonic. But yeah, all these like famous people, and then there's us. But it was just so amazing. Oh my gosh. To be inside the canyon and to see it like that, oh, so beautiful. But I got to play in like slot canyons, and you can see the layers here. What kind of stone is that? Yep, it's sedimentary. In fact, that's all sandstone. Like layer after layer of sand. And it was deposited in these layers, and then the river or the waterfall cut through it later on. And so you can see the different layers in it. But you're walking back, hundreds, millions, up to billions of years ago when you get to the bottom of the canyon. Yep. So usually sedimentary rock breaks on these kind of layers because you get a deposition event, and then maybe billions or millions of years go by and another layer gets put down. So there's missing bits in between here for sure. So that's sedimentary rock. And it happens in episodes. So you'll see this if you get to go caving. There's some spots inside the cave where you can actually see this where it's occurred. Because most of Indiana's rock is sedimentary. Almost all of it. It used to be the bottom of an ancient ocean. So all the crap that settled to the bottom of the ocean sedimented into rock. So that's why all of our rock here has lots of fossils and things like that. But you can actually see the different layers that happened. I drew them on here. In this rock, if we cut back the time, at the bottom here, stuff got deposited like that. See it down there at that layer? And then there was another event here where stuff got deposited. Then another event here, and then at the top, that last layer got put down.
What kind of events cause the layer to form instead of just stuff inside?
Oh, so a lot of the time, there can be a number of different things, but a lot of the time, what happens is you've got transgression and regression of the ocean. So if this was ocean rock, and I don't know, looks like sand. So say the ocean comes in, and we have a beach type environment, and stuff gets put down. And then a million years later, the ocean goes back out. Maybe ice caps form or something, and the ocean gets less, or the ground gets lifted up. And then later on, the ocean comes back in again. So you get and in between, you'll have missing rock. Like we'll know if we find rock somewhere else, oh, there's 2 million years here gone. So when we say the fossil record's incomplete, we know there's chunks missing. It's super obvious. Because any place where there's a layer like that, something stopped and then started up again. But lots of stuff can occur like that. Like you think of, say, modern day Texas with all the deserts and everything. There's loads of rock in Texas. Some of it's from ancient oceans and things. But there's no new rock getting made. Like you think about out here in front of the school, we're not making rock out there. You need a very specific environment to make new rock. Like stuff can die, you can bury your dog out there, but it's not going to be a fossil. You need really certain conditions to have it happen. So what's surprising is that we have the fossils we do have, considering how rare it needs to be to make it happen. We've got a lot of fossils and a lot of layers of rock too. It really is the oldest rock though we don't have as much of. Okay, last type of rock, metamorphic. So a caterpillar undergoes metamorphosis. It metamorphoses into a butterfly, right? So metamorphic rock means to change, to metamorphose, to go from one thing to another, and that's exactly what it is. It's rock that starts out as maybe sedimentary, maybe igneous, maybe metamorphic, and then it gets changed. And there's a couple of ways it can get changed, but the main one is by pressure and temperature. So let's say that magma heats up rock near it, and the contact point where it's touching the rock doesn't totally melt it, but heats it up enough that it chemically changes it. And it can be striking. In fact, something like ugly old limestone can turn into beautiful marble if you squish it and cook it. Different things can give you nice. That's a nice rock right there. I brought some nice, and I brought some marble. Of course I did. So you can start with some ugly thing like limestone, end up with beautiful whites and pinks that are like this purified looking marble just from the limestone. That's nice. There we go. Piece of marble. So marble's actually a pretty good example of a contact metamorphism. And this foliation or banding means like layers or leaves. So this is confusing because we know sedimentary rock forms in layers. Layer after layer after. This one, they just broke like that. It's so perfect. It's a piece of sandstone. But you can see the different colored layers in there from when the sand got put down. Okay? So sedimentary rock, metamorphic rock can have banding. And usually it looks like layers, but it usually does something like this. So picture this thing forming. Got this nice layer of sedimentary rock, and all of a sudden a mountain starts to form. And it gets squished and folded and melted together a little bit. And the minerals literally change, like they reorganize. They grab new ions and change places in chemistry, like it's all chemical happens. And you go from having like these ugly, I don't know, like looking minerals that don't really look like a whole lot, to garnets and like beautiful gemstones that you only find in the mountains. And that's why, because the rock is metamorphosed into new stuff. So it's where we get some of those really amazing things and stuff like that. Metamorphic rocks. There you go. There's some marble. Marble's great stuff. It's really soft rock though, so it's not the greatest thing to put in your house, but it looks really pretty. It's easy to work. Has anybody ever worked rock before? Do you guys do that in art class? No? I'll tell you what, maybe we'll try and work some rock in here. It's kind of fun. You don't work rock in art class? Oh, for crying out loud. It's so much fun. Maybe we might try and carve some rock in here. That'd be a good project. Okay, here's the rock cycle. There it is. So if you want to fill that last question out, here's the 3 types of rocks if you haven't already. Metamorphic, sedimentary, igneous. You know how they form. In fact, it's written right on here. Notice the arrows. Any one kind of rock can turn into the other rock. You can take metamorphic or igneous, grind it up, dip it in some water, let it layer itself, and let it harden together, and you get sedimentary rock. You can take sedimentary or metamorphic rock, melt it, or igneous rock, melt it, re-harden it, and you get igneous rock. You can take any of them, squish them and cook them, and you get metamorphic rock. It's pretty confusing, doesn't it? Like anyone can turn into the other. But what kind of igneous or metamorphic or sedimentary depends on the chemicals that are in it. And it depends on how fast or quick it cools, lots of different things. Cool. Okay, everybody have that. I'll give you a second if you're filling that out.